Now we're going to start with the lecture number 3 for the classical mechanics, and we are discussing for the Newtonian mechanics. That is the topic for your semester BS 5th, and your course code is PHY 509. As we have discussed about the introduction of the classical mechanics, regarding which that classical mechanics is the branch of mechanics under the physics, and it deals with the macroscopic discussion of the objects, and mechanics means the motion of the object and not the cause of the motion, how the we just study that the objects move but not the cause of the object, how that cause of the force, how that object uh, changed its motion, and what kind of causes are appeared there. And in the second lecture we discussed about the frame of reference, and in which we discussed about the space coordinates that are very necessary uh, uh, for the frame of reference, that are necessary for the relative motion of the objects to be observed, in which different kinds of examples were discussed. Now we have to study further for the classical mechanics in our lecture number 3. As we were discussing about the frame of reference we have discussed about the Newton's first law in it. Now in this we our learning objects are uh, uh, rememorizing the Newton's second law and its explanation according to classical mechanics, then Newton's second law and the conservation of the linear momentum. uh, then we will discuss about Newton's third law and the Newton's third law, and how the momentum is conserved according to Newton's third law. Then we will discuss about the torque. After discussing torque and re-memorizing the definition for the torque according to the classical mechanics, what is moment time, then the angular momentum definition. These are the terms we are going to use in classical mechanics, and we have to re-memorize all the definitions according to the classical mechanics. Then the relation between L and L is here angular momentum, and N is here linear moment is the torque. L is the angular momentum and N is here torque representation in classical mechanics. Now afterwards then we will discuss about the conservation of single particle. There are some definitions according to the single particle. Then we have to discuss what is point function.
Imagine you're sitting on a recliner chair watching your favorite movie on a lazy Sunday. And your mom calls out your name and asks you to run some errands. You can imagine how difficult it would be for you to get up and do the work. Imagine you're practicing for your 100 meters race on this track, and somebody asks you to stop immediately within a second. Will you be able to do it? What if you're suddenly asked to turn towards the right? Will you be able to turn immediately? The answer to both the questions would be a no. You can stop, yes, but gradually. You can also turn, but not sharply. And guess what? It's the same story with every object. Every object will continue to do what it's doing. If it's at rest, it will remain at rest. And if it's in motion, it will stay in motion. But what can change this? Yes, only an unbalanced force can change this. If it's at rest and an unbalanced force acts on it, it will move. If it's in constant motion and an unbalanced force acts on it, it may accelerate or change direction. And this is nothing but the Newton's first law of motion. Here's the correct definition. An object at rest stays at rest, and an object in motion stays in motion with the same speed and the same direction, unless acted upon by an unbalanced force. In simple words, it means that the objects continue to do what they're doing unless some external unbalanced force acts on them. We can also understand this using a simple diagram. If the forces are balanced, there can be two cases. An object may be at rest, or an object will be in motion at a non-zero constant velocity in a particular direction. These can be the only two cases when the forces are balanced. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced.
Momentum, we can say that Newton's second law can be stated as time rate of change of momentum that is equal to force, and according to Newton's second law, that is represented as F is equal to P dot on the above of the P sign with the vector. You know that mm, you know that for the first differential order we draw a single dot on the um, symbol of the uh, vector form, and that p dot will be equal to dp over dt. We will give it the equation number 1. Now to express the second law of motion in terms of the acceleration, we write the linear momentum as a product of mass and velocity. We know that linear momentum p vector is equal to mv vector. Now putting this equation of p in the previous equation 1, we get d over dt into mv. As mass is constant, that cannot be differentiated, so it can be written out of the differential d by dt. Then the equation will become F is equal to m into dv over dt. Velocity is the vector form, and f here is also the vector form. So f is vector sign is equal to m into a. You know that acceleration is equal to dv over dt, that is equal to a, so f is equal to ma. That is the definition we are being studied from the previous classes. F is equal to ma. So we can state that acceleration of an object depends on its mass and on the net force applied on the body. You can say that the mass, greater is the acceleration and greater is the force applied for the body, and smaller the mass, smaller the acceleration, smaller force is needed to stop or um, um, uh, take it in the motion of that object. Now in classical regime, both laws are valid, but in relativity and quantum mechanics, second law is modified as speed approaches to c. In classical mechanics and in the way of studying the objects in the macroscopic view, the both laws for the Newton second law, F is equal to dp over dt and F is equal to ma, are valid. But in quantum mechanics and if we are discussing for the relativity process, the second law cannot be directly applied on the objects, but it is modified for in simple acceleration or velocity is modified in the speed approaches to c. And here you can see that c, you know, that is equal to speed of light, which is equal to 3 into 8 10 raised to power 8 meter per second. As in special relativity, at high speed the approximation the momentum is the product of mass and velocity is not accurate. As in simple way, we say that momentum is equal to mass and velocity, but I mean if we are dealing with the high speed objects, as the speed is approaching the speed of light, so in special relativity the momentum is not directly equal to mass and velocity, product of mass and velocity at speeds comparable to the speed of light. The second law holds in original form. F is equal to dp over dt, where f is equal to p. F and p are four vectors, then that is equal to four vectors. Now you can see the example for F is equal to ma, that there is a mass of m and there are two forces being applied on the object. One is the F1 force that is applied on the mass in the right direction to stretch is forward, and there is a F2 force that is acting on some angle, and the sum of two vectors uh, will be summation F, and that is will be equal to the acceleration provided on the body, and that is equal to A is equal to summation F by T. You can see in the figure, you can state that acceleration due to the net force. Here you can see the example for the Newton's second law. If you apply more force to an object, it accelerates at a higher rate. You see that the object and the mass are of the same mass, and the person is applying some force on the object, and it is accelerating with some speed. It is accelerating, and the speed increases. And up in the second picture, you see that as the force is applied more, then the same object moves with the same more acceleration, and the speed also increases furthermore. Let us assume that we have an aeroplane at a point O, defined its location x naught and time t naught. The aeroplane has a mass of m naught and travels at a velocity of v naught. In the right hand side picture you can see that an external force F to the aeroplane shown above move its point to the point 1. The aeroplane's new location is x1 and the time is t1. So the mass and the velocity of the aeroplane change during the flight to value m1 and m1 and v1. Newton's second law can help us determine the new values of v1 and m1 if we know how big the force F is. Let us take the difference between the two coordinates at the point 1 and the coordinate at point O. We can write F is equal to m1 into v1 minus m naught into v naught divided by t1 minus t naught. According to Newton's second law, talks about changes in momentum mv. So at this point we can't separate how much the mass changed and how much the velocity changed. We only know that how much product m cross v changed. As we cannot separately tell that mass and velocity how much changed, so we only discuss about the mass and velocity product, that is momentum, the change. Now let us assume that the mass stays at a constant value equal to m. This assumption is rather good for an airplane because only change in mass would be for the fuel burned between the point 1 and point 0. The weight of the fuel is probably small relative to the weight of the rest of the airplane, especially if we only look at small changes in time. If if we were discussing the flight of a baseball, then certainly the mass means constant, but if the remains constant. But if we were discussing of the flight of a helicopter, then the mass does not remain constant. We can only look at change in the momentums. So for a constant mass m, Newton's second law looks like F is equal to m cross into v1 minus v naught divided by t1 minus t naught. The change in velocity divided by change in time is the definition of the acceleration. So the second law will reduce to the more familiar product of the mass and acceleration, that is F is equal to ma. Force is equal to mass into acceleration. Here velocity, acceleration, momentum and force are the vector quantities. Remember that this relation is a good for objects that have constant mass. This equation tells us that an object subjected to an external force will accelerate and the amount of the acceleration is proportional to the size of the force. The amount of the acceleration is also inversely proportional to the mass of the object. For equal forces, a heavier object will experience less acceleration than a lighter object. Considering the momentum equation, a force causes a change in velocity and likewise a change in velocity generates a force. The equation works both a way. The velocity, force, acceleration, momentum have both a magnitude and direction associated with them. Scientists and mathematicians call this a vector quantity. This quantity shows here are actually vector quantities and can be applied in each of the component of the direction. We have only looked at one direction and in one direction and in the amount of the acceleration proportional to the size of the force. The amount of the acceleration is also inversely proportional to the mass of the object. For equal forces, a heavier object will experience a lesser acceleration than a lighter object. Considering the momentum equation, a force causes a change in velocity and likewise a change in velocity generates a force. The velocity, force, acceleration and momentum have both a magnitude and direction associated with them. Scientists mathematicians call them vector quantity. The quantities shows here are actually vector equation and can be applied in each of the component directions. We have only looked in the one direction and in general an object moves in all three directions: up, down, light, right, left, forward and back. Now
Do you remember the Newton's first law of motion? It says that an object will continue to do what it's doing unless acted upon by an unbalanced force or some net force. Now the important question is, what happens when there is net force acting on an object? That's precisely what the second law of motion will discuss. Do you remember understanding the first law of motion with a simple diagram? If the forces are balanced, the acceleration will be zero. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced, only if the net force is zero. Now let's try to create a similar diagram for the second case. If the forces are unbalanced, then there will be acceleration. We saw that in the previous video. And now we come to the interesting part. Let me ask you a question and I'm sure you can answer it. On which two factors do you think the acceleration will depend on? I want you to tax your brain a bit. Let me repeat my question. On which two factors do you think will the acceleration depend on? Okay, let's say there's an object on a table. You apply a net force of 10 units on it. And then you apply a net force of 20 units on it. In which case do you think the acceleration will be more? Of course, the one in which the force was more. So we can say that one of the things the acceleration depends on is net force. If it's more, then more will be the acceleration. If it's less, then lesser will be the acceleration. Acceleration depends directly on the net force. Come on, now I want you to think about the second quantity the acceleration will depend on. Let's say there are two objects on the table. One has a mass of 3 kilograms and the other has a mass of 5 kilograms. Now, if you apply net force of 10 units to each of them, which one do you think will accelerate more? Surely it's the 3 kg one because it has lesser mass. Lesser the mass, more the acceleration. And more the mass, lesser the acceleration. Hence, we can say that acceleration depends inversely on the object's mass. If you understand this concept well, then understanding the second law of motion will be very easy. Mathematically, it can be written like this. In simple terms, the acceleration is directly proportional to the net force applied and inversely proportional to the mass of the object. That's the second law. Or as more people understand it, like this. The net force is the product of mass and acceleration. With this, can you tell me the units of force? That should be easy. The standard unit of mass is kilograms, and that of acceleration is meters per second squared. So the unit of force is kilograms times meters per second squared. And this is what we call as Newton. 1 Newton is 1 kilogram times meters per second squared. So if the mass of the object is 10 kilograms and the acceleration is 10 meters per second squared, then the force will equal 100 newtons. We can say that 1 newton is defined as the amount of force required to give a 1 kilogram mass and acceleration of 1 meter per second squared.
Examples of force involving aerodynamics are an aircraft motion resulting from an aerodynamic forces, aircraft weight and the thrust. Now we have to start Newton's second law and how Newton's second law conserves the linear momentum. First, Newton's second law also gives the acceleration of the linear momentum. Consider there is no net force acting on a body. Then the Newton's second law gives F is equal to dp over dt. We have studied in the previous slide that F is equal to dp over t. If we say that there is no force acting on the body, then here F is equal to 0. Substituting the value for F is equal to 0, that becomes 0 is equal to dp over dt, and here we integrate both sides and we get according to the time with respect to time, and we get p is equal to constant. That shows that the Newton's second law conserves the linear momentum. There is no change in the linear momentum according to the Newton's second law, and they are relative to each other. So we can say that the linear momentum conserves with time. We have seen that linear momentum has been conserved with time after integrating. Now we have to discuss about the Newton's third law. You know that we have studied that there in simple definition we have studied that if a force is applied on the body, there is an equal and net force opposite on the body to the applied force. So we can say that two bodies exert force on each other which are equal in magnitude but opposite in direction. If there is some kind of any object present, then there are two kind of forces being applied on it. One is from the object, from the downward in the upward direction, and in the object on upward, placing a downward force on the object in the downward direction. The two forces represent a mutual interaction of two objects and each act on a different object. We can see a figure in the next slide. Here you can see the example of a table and a book. You can see that book is placing a downward direction of the weight, that is W is equal to mg, that is weight of the book, in the downward direction, that is the action, and the table is placing a reaction force in the upward direction, that is the normal force. So we can say that is the action and reaction pair, which is according to the Newton's third law. You can see that book is applying action force in the downward direction, that is F1, and the table is producing a opposite reaction force in the upward direction, that is F2. So we can say that action reaction force, they are opposite in direction but equal in magnitude, so F1 is equal to minus F2. So according to Newton's law, we know that F is equal to dp over dt. So for the above equations, we can write two equations. For F1, that is dp1 over dt, and for F2, that is equal to dp over dt. With the minus sign, substituting the values, we see that dp1 over dt is equal to minus dp2 over dt. We know that linear momentum is equal to mv. So for P1, that is M1 V1, and for P2, that is M2 V2. We know that mass is constant, so that cannot be placed in the differential form d by dt, that is taken out of the differential form. So M1 d1 over dt is equal to minus M2 dv2 over dt. We know that dv over dt is the acceleration, so here dv1 over dt will give acceleration 1 a1, that will become m1 a1, and is equal to minus m2 dv2 over dt, that gives a2, that is the acceleration of the second object reaction force. So a2 will be equal to dv2 over dt, so that gives minus m2 a2, that equations become m1 a1 is equal to minus m2 a2. By this rearranging the equation, we get m2 over m1 is equal to minus m1 over minus a1 over a2, that are the ratios of the two masses with respect to each other. From the previous equation, m2 over m1 is equal to minus a1 over a2, we see that ratio of the masses of the two objects is equal to the negative of inverse of the acceleration. Now the negative sign shows that the accelerations are opposite. For example, action and reaction forces by book and table respectively, as shown in the previous figure in the above slide. They are the quite example of the action reaction force according to Newton's third law. Now the examples of action and reaction involving the aerodynamics are the motion of the lift from an airfoil. The air is deflected downward by the airfoil's action, and in reaction the wings is pushed upward. Number 2, the motion of a spinning ball. The air is deflected to one side and the ball reacts by the moving in the opposite direction. Number 3, the motion of a jet engine produces thrust and hot exhaust gases flow out of the back of the engine, and a thrusting force is produced in the opposite direction.
The only question you need to ask yourself while studying the third law is, what happens when two objects interact with each other? What happens when you place an object on the table? The object exerts a force on the table and the subject exerts an upward force on the object. There are two forces that result from this interaction: a force on the table and a force on the object. The magnitudes of the two forces are the same, but the directions are opposite. These forces are called as action and reaction forces. The force exerted by the object on the table was an action force, and the force exerted by the table on the object is the reaction force. What we saw here is nothing but a display of the Newton's third law of motion. Every action has an equal and opposite reaction. That's how simple the third law is. Every action has an equal and opposite reaction. It means that when two objects interact, there is a force on each object. The magnitude of force on the first object equals the magnitude of force on the second one. And what about the direction? The direction of force on the first object is opposite to the direction of force on the second one. Let's talk about more examples. While a frog is swimming, it pushes the water back and the water pushes its body forward. Now let me ask you a question. Say a bird is flying upwards. Will the Newton's third law apply here? Sometimes the third law is not so obvious. You'd probably say that the bird is the only object here and there's no second object. But that's not correct. The wings of the bird push the air downwards and the air pushes the bird upwards. Action and reaction forces make it possible for birds to fly. We take one last example to understand something very interesting about the third law. What happens when a gun is fired? You're right, it exerts a forward force on the bullet. And the bullet exerts an equal and opposite reaction force on the gun. And this exists in recoil of the gun. A perfect example of Newton's third law. But hold on. If the force exerted by the gun on the bullet is the same as the force exerted by the bullet on the gun, then why doesn't the gun recoil with the same acceleration as the bullet? The gun recoils, yes, but it doesn't recoil at the same acceleration as the bullet, right? Same magnitude of forces, but different accelerations. Why do you think this happens? Okay, so if your concept of the second law of motion was clear, you wouldn't really be surprised with this. The second law of motion says that the force is the product of the object's mass and acceleration. Or the acceleration of the object is equal to the force over its mass. What does this tell us? Yes, if the mass is more, then the acceleration will be less. In this example, the mass of the gun is much more than that of the bullet. Hence, the acceleration of the rifle is lesser than that of the bullet. If you're in a boat and step out of it onto the land, there are two forces involved. You pushing the boat behind and the boat pushing you forward. And that's why you see the boat go behind when you go forward. Now let's say a sailor jumps off a huge ship. The sailor does apply a force on the ship and the ship also applies a force on the sailor. But do you think the ship will accelerate as much as the sailor? Not really. And I think you know why.
Now, giving a review for the Newton's laws of the motion, three laws of the motion. First one is Newton's law of motion, that is for inertia. An object of rest remains at rest, and an object in motion remains in motion at constant speed and in a straight line unless acted by an unbalanced force. Number two, the second law, Newton's second law of motion, that is force. The acceleration of an object depends on the mass of the object and the amount of the force applied. Number three, the Newton's third law, that is action and reaction. Whether an object exerts a force on another object, the second object exerts an equal and opposite force on the first object. Now, according to Newton's third law, we can also conserve the linear momentum. We know that Newton's third law also gives the conservation of linear momentum as the Newton's second law. So we say that Newton's third law is stated for the two isolated bodies 1 and 2, F1 is equal to minus F2. Using the definition of the forces as given by the Newton's second law, which is F is equal to dp over dt. So dp1 over dt is equal to minus dp2 over dt, and taking the negative side of negative dp2 over dt on the right hand side to the left hand side, that is dp1 over dt plus dp2 over dt is equal to 0. Taking the differential common outside, that is d over dt into the bracket p1 plus p2 is equal to 0. Then that gives p1 plus p2 is equal to constant. So that shows that the linear momentum conserved with time. So we can say that Newton's third law can also be conserved with the time for the linear momentum. Now the another term we have to discuss for the classical mechanics, that all these things are being used in the classical mechanics. So we say that if a body is fixed at a certain point O about which it can rotate, that is called torque. If a force F is applied on a body, and or we can say that rotating force is called the torque. So if a force F is applied on the body and the body rotates in its body rotates along its own axis, or this rotational tendency of the body due to the force F or the turning effect of the force F is known as the torque or the moment force. So we can write as torque N vector is equal to R moment arm multiplied by cross product with the force F vector. Here you can see that there is a ball with a rod attached with the nut on the circular pivot, and you can see there is a velocity v on the ball that is tending to move that ball in the rotational form, and there is a moment arm with the red arrow, and there is a angular force on the pivot on the upward direction and on opposite direction. So we can say that torque is equal to r cross f, and the angular momentum L is equal to R cross P. Angular momentum is the product of moment arm and the linear momentum P. This shows the torque of or the moment force or the turning effect, that is called torque. Now for this we discuss the definition for the moment time. It is the perpendicular distance between the line of the action of the force and the axis of rotation, and that is called moment time. And for the angular momentum we have the definition moment of linear momentum, that is called angular momentum. L is equal to R cross P, and substituting the value for P, L is equal to mr into R cross mv, as mass is constant and that cannot be cross product. So L is equal to m into R cross v. Substituting the value, we have substituted the value of P is equal to mv. Now we will discuss here the relation between the angular momentum and the torque. We have two equations. First one is for the angular momentum, L is equal to R cross P, and that is given the equation number 1. Second is the torque equation, N is equal to R cross F, and differentiating these two equations, first differentiating the equation number 1, that is dl over dt is equal to d by dt into R cross P, as d over dt into R cross P is the product. So we will apply the product rule on the right hand side, that will give dl over dt is equal to dp over dt cross r and plus dr over dt cross p, and dl over dt will be equal to dp, dp over dt will be equal to force, so that will become r cross f, plus dr over dt will be equal to v, and p is equal to mv. We know that the cross product with the two same vectors is not possible, that is equal to 0, since v is equal to dr over dt, p is equal to mv, f is equal to d by dp over dt. So we can write v cross mv is equal to m into v cross v. I told you that v cross v is not possible for the same vectors with the cross product, so that will be equal to 0. So the above equation will become r cross f is equal to n, and n is the torque. So we can write, substitute this value in the above equation with the dl over dt into r cross f, and that is torque. So dl over dt is equal to torque n plus 0. So we can say that torque is equal to dl over dt. We can say that rate of change of angular momentum gives the torque.
ये वाला और ये वाई एक्सिस और ये जेड एक्सिस, ये एक्सिस आप अपनी मर्जी से कुछ भी चेंज कर सकते हो।
Now here
वेलकम टू
हमारे
माय
पास
यूट्यूब
अब
चैनल
we have
फिजिक्स वंडर्स।
three axes x, y, z, or then there is a point P having mass m. We draw a position vector for it from the origin O, that is the point P that is located in the xyz coordinate system. We draw a vector, position vector, to find the location of that point, that is designated by r vector, and the mass of that point is m. Here we can write r is the position vector. The position of position of the point P is located from the region O. So for velocity we can write dr over dt. Now acceleration is equal to dv over dt, and in the place of v we can write the value of above v is equal to dr over dt. So we have d by dt into dr over dt. So we can write, substituting the value from above equation 1, dr over dt, then here d square r over dt square, giving it equation number 2. Now we are writing, for the conservation of linear momentum, now we will write, according to Newton's second law, of motion, in the terms of linear momentum, that is equal to F is equal to dp over dt, rate of change of linear momentum, giving it equation number 3, and writing for p is equal to mv. The above equation 3 becomes d by dt into mv, and m is constant, so we will take it out of the differential. So we can write m dv over dt, as we know that dv over dt is equal to acceleration, and acceleration was equal to d square r over dt square. The equation becomes F is equal to ma, which is Newton's second law. This is the general form of Newton's second law. Equation 3, F is equal to dp over dt is actually equal to F is equal to ma. Both equations are for designation of Newton's second law of motion. We will again write F maximum is equal to dp over dt, dp over dt, if F net or F maximum is equal to 0, then dp over dt will equal to 0. So integrating the equation, we get p is equal to constant. That means the linear momentum is constant, mean conserved. Now the second part is the conservation of angular momentum. We will write for angular momentum L, that is equal to I omega, and I is equal to moment of inertia, and its value is equal to mr square, and omega is angular velocity. So we can write the another form of angular momentum, L is equal to r cos p. Taking a coordinate system, two axes x and y, taking a curved path with the point P as the first point and a second point P2. The position vector for point P1 is r, and for after some interval of time after covering theta distance, it is reached at point P. Now L is equal to r cross P. Differentiating this equation with respect to t, that will become dl over dt is equal to d into d over dt into r cross p. That is a cross product, so we have to differentiate one by one, applying the product rule for the differentiation. So here, applying the product rule, d over dt uv is equal to du over dt dot v plus dv over dt dot u. Applying on the above equation 2, that becomes dl over dt is equal to dr over dt dot cross p, as there is a cross product. Cross p plus r vector cross dp over dt as we know that P is equal to mv. So the second term and dr over dt is equal to velocity dr over dt, and force is equal to dp over dt according to Newton's second law of motion. Giving in the equation number 3, then using these equations in equation number these values in equation number 3, we get dl over dt is equal to v cross p and p is equal to mv v cross mv plus r cross f. As we know that I dot I j dot j k dot k is equal to 1 and I cross I j cross j k cross k is equal to 0. So same, we can say the vector product of same two vectors is not possible. So the first term above will become equal to 0, writing the caps on the unit vectors and giving the equation number 4. And for the first term we can write v cross v is equal to 0 and taking the mass out of the cross product, that will become m into v cross v is equal to 0. Then we can write dl over dt is equal to 0 plus r cross f, and we know that r cross f is equal to torque, and here we are representing I have told you that we are representing the torque in the n with the n symbol. So we can here first of all write tau for dl over dt is equal to tau, that tau is equal to n, that is a torque external force applied for the rotational motion. So dl over dt is equal to tau, that means the torque is related to the angular momentum, rate of change of angular momentum. So if we take the different, if the torque is 0, then if the angular torque is 0 or the rotational torque or the rotational force is 0, then the dl over dt term will also be conserved, writing dl over dt is equal to constant is equal to 0, and integrating that equation we will get L is equal to constant. So here we can see that angular momentum will be also equal to constant and L will be conserved. That means uh, both linear and angular momentum are conserved with um, in according to Newton's second law and third law, and both torque and angular momentum are related to each other. Conservation of single particle. For this we have to discuss for linear momentum the law of conservation of linear momentum for a single particle. If the total force acting on a particle is 0, then the linear momentum is conserved. As classical mechanics deal with the macro particles, means that the single particle and a system of particle is considered as a one system. So when a total force is acting on a particle is 0, then the linear momentum will be conserved, and that is discussed previous as f is equal to dp over dt. Now for the law of conservation of angular momentum for the single particle, if the total torque n is acting on a particle is 0, then the angular momentum will also be conserved. If the torque n is equal to 0, then the angular momentum dl over dt is equal to torque, then n is equal to 0. Substituting this value, we get dl over dt is equal to 0. Then integrating this term dl over dt, we get L is equal to constant. Now for different definitions for the single particle, first of all, the first definition is for the point function. A function that depends upon the location of a point is known as a point function. For example, electric intensity, potential energy, etc. Now the second definition for the point function is the scalar point function. You know that the scalar value is that value that which have magnitude but not the direction. So a point function which has the magnitude is called a scalar point function, such that example is potential energy etc. And the other definition is vector point function. A point function which has a magnitude as well as a direction is called a vector point function, and that the example will be electric intensity etc. Now for the fourth definition, curl of a vector, how can we take a curl of a vector? For the curl of a vector, we take a cross product and operator, del operator, that is del cross f. We get write the determinant of that is I j k, and in the below I cap we write partial over partial x, and in the j in partial over partial y, under k we write partial over partial z. Then force have three component fx, fy and fz. We substitute here. After placing this value, we can open the determinant. That determinant can be opened and written as del cross f is equal to I cap into partial fz over partial y minus partial y over partial z, bracket close, minus j cap into partial fz over partial x minus partial fx over partial z, bracket close, plus k cap into partial fy over partial x minus partial fx over partial y, bracket close. Now for the last definition for the Stokes theorem. The Stokes theorem mathematically is written as integral curl integral closed integral f dot dl is equal to here f dot dl is a line integral, and when we place a curl on an integral, that is a closed integral, that is equal to integral of surface s is into curl f, that is del operator cross f dot d and ds. That is the formula for the Stokes theorem. If here is the Stokes theorem, if it states that the circulation of a vector field A around a closed path is equal to the integral of del cross A over the surface touched by the path, then we can write closed integral L A dot dl is equal to integral of surface del cross A vector dot ds. That is the definition for Stokes theorem. And writing for the del cross A, for the surface we can write the equation by this A dot dl, that are the vectors, and there is a dot product between, and then that is equal to curl of cross f dot ds. That is the relation between the integral surface and the line integral. So by equating this equation, we have that equation curl of or del cross A dot ds. Now the line integral is equal to a, we have considered a vector, its value is x, y cap, and y vector plus y j cap. Here is a graphic figure where are some point values. For line integral we will calculate a dot dl, and dl is equal integral of a dot dl, and we have dl is equal to dx I cap plus dy j cap. Here a dot dl will be equal to dot product between the two values. We can write for the integral closed integral xy dx plus integral of y square j cap y square dy. Substituting the values and solving it, we get for the closed path a b c d. We have written the integrals for four paths a b b c c d and d a. We see that the values can be calculated on the paths A, B, B, C, C, D, cancelling the equation for the path B, C and B, A that are the same, and cancelling the integral for A, B with the integral of C, B. Then writing the integrals, remaining integrals and solving, we get x square by 2 plus 4 integrals, and we get the value of minus 12. Now we get solving for the surface integral. The integral A dot ds. Here the value of ds is equal to dx dy I cap. Here is a closed path in the xyz coordinate with the path a b c d. So integral of del cross A dot ds will be equal to double integral x k cap dot dx dy k cap. Solving that equation by the taking that the vector quantity, you know that a third vector quantity is upward by right hand rule. So solving that for the path a b b c c d, we know that the integrals will be written and solved for the integral. By opening the determinant for del cross a, we get the same value by solving that integral, minus 12. Now you can uh, uh, understand and write that Stokes theorem. To prove that Stokes theorem is line integral is equal to the surface integral, closed path of line integral A dot dl will be equal to surface integral del cross A and dot ds, and will be the unit vector of that surface. Hence this equation is proved. The double integrals are opened here for the two paths A, B, B, C. So we get after solving minus 12. So we can see that the line integral is equal to the surface integral minus 12 minus 12. So we have proved the Stokes theorem that closed integral of line closed path of line integral will be. These are the different references of for the classical mechanics topic we have discussed here. Or you can follow this. If there is any problem, you can ask me. Thank you.